Why doesn't gold rust? Hey, engineering enthusiasts! Do you know why an inherited piece of jewelry keeps shining for decades, while a forgotten nail in the backyard falls apart in rust? This question begins a story that reaches laboratories, mines, and satellites. Today, you will find out in a clear and practical way why gold is so resistant to corrosion and how this property shapes engineered solutions that range from your smartphone to outer space. But first, what exactly is rusting and why doesn't it happen to gold? Rust is the common name for the corrosion of iron and steel, when metallic iron forms hydrated oxides and breaks down into fragile flakes. Gold, on the other hand, is a noble metal, and under ambient conditions it hardly reacts with oxygen and water, doesn't form an unstable oxide layer, and remains metallic and shiny. In other words, gold doesn't rust because rust is a phenomenon of iron, and gold is extraordinarily resistant to corrosion. And what is the chemical composition of gold, and how does that explain its resistance? In its pure form, or 24-karat gold, gold atoms arrange themselves in a compact and stable metallic lattice. Its electronic configuration and noble character make gold have little tendency to lose electrons to form oxides. In air or in water, the surface does not degrade. It remains metallic, dense, and cohesive, preserving its appearance and properties. Gold hardly reacts. It is stable, even when everything around it tends to corrode. And that's its nobility. Now think about this as a career. What if your journey could be like that? A solid, resistant to pressure, while others oxidize over time. But getting back to the subject, when we talk about jewelry gold with other alloys in jewelry and technical applications, gold is often alloyed with silver, copper, palladium, nickel, and other elements to adjust color, hardness, and cost. In 18-karat gold, for example, gold makes up 75% of the alloy, and in 14-karat gold, it contains about 58.5% of the alloy. These alloy metals can, over time, darken slightly, resulting in a superficial tarnish. But the gold itself remains chemically stable. Often, the surface tends to become enriched with gold, serving as a protective layer for the other elements in the alloy, which helps maintain its shine and resistance to corrosion. But what physical properties of gold help with its durability in the real world? Well, gold is highly malleable and ductile. It can be made into very thin sheets or drawn into wires without breaking. This brings an indirect advantage to its durability. Where other materials would form microcracks that accelerate corrosion, gold deforms without cracking its surface layers. In addition, it has excellent electrical and thermal conductivity, chemical stability in harsh environments, and does not suffer from embrittlement by brittle oxides. Although it is relatively soft when pure, it does not degrade by corrosion. It can only be scratched, but scratching is not the same as oxidizing. And how is gold's resistance to oxidation used in engineering? In connectors and critical contacts, the stability of gold is literally gold. By not forming insulating oxides on its surface, gold keeps the contact resistance low and predictable over time. This reduces intermittent failures due to what we call fretting corrosion and ensures reliability under vibration, humidity, and thermal cycles. Not by chance, pins and blades of high reliability connectors receive gold plating with controlled thickness. And on printed circuit boards or PCBs, why do we see gold on these boards? Well, modern PCBs use processes like electroless nickel immersion gold or electroless nickel immersion gold. The nickel acts as a barrier and the gold in a very thin layer, typically in the range of 0.05 to 0.125 micrometers. It protects against oxidation and ensures good solderability and stable contact until final assembly. This thin layer isn't there to conduct better than copper, but to prevent oxidation, where the connection needs to be perfect from the very first contact. Besides electronics, where else does the nobility of gold make a difference? In aerospace environments, the chemical inertness and optical properties of gold are valuable. It reflects infrared very well and withstands extreme environments of vacuum, radiation, and thermal variations. Mirrors and filters receive ultra-thin gold coatings to optimize the collection of infrared radiation and maintain performance over the years. The message to the engineer is clear, where chemical stability, interface consistency, and long-term reliability are mandatory. Gold is the natural candidate. What's the most famous space example, and why does it use gold? An iconic case is the James Webb Space Telescope, whose hexagonal mirrors were coated with a layer of gold about 100 nanometers thick. To maximize infrared reflectivity, it's enough gold to improve the signal at critical wavelengths, but thin enough to save on mass and cost. And the secret is that gold doesn't degrade during operation, preserving optical performance mission after mission. But is gold invincible to corrosion in every scenario? Well, no. Gold resists very well under everyday conditions, but it can be dissolved in specific chemical environments. The classic aqua regia, which is a mixture of nitric acid and hydrochloric acid, oxidizes and chlorinates gold. In mining, there's the gold cyanidation process. It uses oxygen and cyanide to form the soluble complex known as the cyanoaurate, and today it's one of the methods used to extract gold from low-grade ore. In other words, gold doesn't rust, but it can be corroded by specific and controlled chemical processes. But what if I use gold in my daily life? Is there anything practical to consider? In jewelry, pure gold doesn't tarnish. However, less pure alloys can darken slightly because of the copper or silver present. Cleaning gently with mild soap and warm water is usually sufficient. For components, the thickness of the gold coating needs to match the wear conditions, such as the number of insertions, the environment, and vibration. Gold that is too thin loses performance due to abrasion, and gold of lower purity loses stability. So, finding the right balance is better for cost effectiveness. In engineering, chemical stability is not a luxury, it's a foundation of performance. If you've made it this far and enjoyed the video, take a moment to subscribe if you haven't already, leave your like, and turn on the notification bell. And if you find our content interesting, consider becoming a member to help us keep producing content here on the platform and to be mentioned in our videos. And did you know why gold doesn't rust? Do you have any gold objects there? Share it in the comments, I want to know. On the side, there are 2 videos you should watch to expand your knowledge and curiosity. And if you want to support us, leave your like, subscribe to the channel, turn on the notification bell, and consider becoming a channel member. That's it, engineering enthusiasts, a big hug, and I'll see you in the next video.